Today we're going to explore the mathematical and physical properties of this model rocket to figure out how rocket science works. This is what the trajectory of the rocket will look like throughout the launch. And there are three main periods of the launch that we're going to be concerned with. The first one is the thrust period, in which the engine is burning its fuel to lift the rocket. And the second one is the coast period, where the rocket has used all of its fuel, but it's still going up because gravity has not yet accelerated it into a negative velocity. And the third is the descent stage, which is not really so important to our calculations. But there is some interesting quirks to this, because before the engine stops burning, it actually does begin to accelerate downward. And this is because the force of thrust, becomes less of a force than the gravity. And we know that if a force is overpowering another force, then it will begin to accelerate into the direction of the larger force. And then after this thrust is no longer present, then the rocket will just begin to accelerate at 9.8 meters per second squared downward.
Divided by 3.
Alright, it's filming now.
Ready?
Yeah.
You gotta do fire in the hole. We're
Yes.
good. I don't know how long we have until it's gonna go. Oh my god. Shit. I'm definitely gonna mess this up. I'm not ready for it. What if it kills Mike?
What if it explodes?
Yeah.
Yeah.
And we had it. Shit!
Where did it go?
That's way too high, dude. Oh, I got it.
I don't know. Oh yeah, I got it.
I got 60. Yeah, I got 61. That's not too, that's not bad. Yeah, 61. Wait, what just happened? Oh, look at the thing. Where's it going? It's over there.
I sure hope I'm getting this.
It's gonna go. Joe, where are you going? Of all the places it could have gone, it goes right in the ground. Wait, do we have to retrieve it?
So now we're going to calculate the burnout velocity of the rocket. And as Mike mentioned before, burnout is the point the rocket reaches when it's used up all its rocket fuel. The thrust is given by this graph. The thrust of the engine is given by this graph. That was found on the manufacturer's label. The equation for burnout velocity is given here, in which Q is the terminal velocity, H is a coefficient, and T is the time it takes the engine to burn all of its fuel. To solve for this equation, we need Q, which is given here. T is the average thrust of the graph, M is the mass of the rocket, and G is the gravitational acceleration, and K is the coefficient of air resistance. K is given by this equation, where P is the density of air, C is the drag coefficient, and A is the cross-sectional area of the rocket. Now normally to find average thrust, we would use the mean value theorem of calculus, in which you take the integral of the graph and divide it by the interval. Now we found online that the impulse for this rocket was 5 Newton seconds, and we divided it by the time it took the rocket to burn all of its fuel, which was 1.1 second. And that gave us an average thrust of 4.5 newtons. So now we started to plug all of our values into our equations. And for K, we got 2.4 times 10 to the negative 4th kilograms per meter. For Q, we calculated that the terminal velocity was 127 meters per second. And the H, our coefficient, was 0.92 inverse seconds. Using all these values that we calculated, we plugged it back into the burnout velocity equation and got 59 meters per second.
Now that we've solved for the burnout velocity, we can estimate the height achieved during the burn period and the coast period. For the burn period, we're going to use the average mass, or the initial mass plus the final mass divided by 2. The average thrust, which is the average value of the graph, the K value that we solved for before, and finally this burn velocity that we just solved for. So here are the values here, and plugging them all into this equation gives you 33.6 meters. And then now we have an equation for the height achieved during the coast period, and it looks very similar, except we're going to be using a different mass here, and this will just be the final mass. the k value will be the same, and the velocity will be the same. Plugging in these values give you 114 meters, which we then add to the burnout height, and we get 147.6 meters. It's evident that there is a large discrepancy in our data. We observed the height to be about 96 meters. We calculated the height to be about 147.6 meters, yet the box says that the rocket should achieve about 129 meters using the B4 engine. So you might say, Mike, why is there such this large difference between them? And there's a multitude of reasons for that. For one, it's not too unlikely that the box overestimates how high it will go just to get more people to buy it. And another reason is that the equations that we use assume a much more massive rocket, which will have much less of an effect on it from wind resistance, because the force of gravity will be so much more impactful. So it's not unlikely that the equations that assume straight up height overestimate how high it's going to go, because the rocket sways from side to side and even somewhat downward because of the wind resistance. Ultimately, the math that we did today is not rocket science. Once you get into much bigger launches, there are a lot more changing variables as you ascend through Earth's atmosphere. And two of these, for example, will be the force of gravitation and the air density. If we look at this equation, force equals gravitational parameter times the mass of the Earth times the mass of the rocket divided by the radius squared, and we derive both sides, it becomes apparent that you're going to need a lot of instrumentation to measure a lot of things, like the instantaneous rate of change of the radius, which depends on your speed and angle, and the instantaneous radius away from the center of the Earth. When we look at air density, it becomes even more apparent because there are so many changing variables, like the change in temperature and the change in absolute pressure, and it becomes way out of proportion. Meanwhile, our model rocket science barely even required an integral.
Rockets are pretty cool.